Welcome and thank you for joining us. You're here at the American Association for the Advancement of Sciences webinar on advances in PFAS destruction. I'm Rebecca Eicher. I'm a project director with the EPI Center at AAAS, so the Center for Scientific Evidence in Public Issues. We welcome you all, and we'll get started by inviting our partner Resolve to join us, Maya Breitberg-Smith, who will be moderating and facilitating today's discussion. So I'm just going to pass it right over to her as we get started with this exciting discussion.
Great. Well, thank you, Rebecca, and really glad to see so many folks joining the webinar today. As we're getting started here, I would just invite everyone who's joining. One of the challenging things about Zoom webinar is that you can't see who else is on the webinar. So as we're getting started, I wanted to invite all of you who are joining us to go ahead and introduce yourself using the chat. Go ahead and put your name, organization, where you're coming from into the chat. And also we wanted to just do a quick poll as we're getting started for you to introduce yourself, kind of share what sector you're in, just again to help us all get a flavor for who is joining us on the webinar today. So as we're getting started, I'm going to go ahead and share the agenda so you can get a sense for what we're planning to do during the session today. So as you might have read in the invitation and registration information, we know that the destruction of PFAS contaminants is a really complex issue that many decision makers across the country are wrestling with. And so today's webinar is really focused on sharing some of the advances in science and PFAS destruction, including some of the emerging technologies, and with a goal of supporting decision makers in your states and communities. And also during the session, we want to help build a network of scientific and PFAS destruction experts to continue all of your abilities to kind of engage and think through this issue moving forward. So we'll start out after a few introductory remarks with a presentation from Rebecca Eicher, who you just met, kind of on an overview of the destruction, PFAS destruction needs, challenges, use cases, and she'll also do a bit of an introduction to the state of the science. And then following her introduction, we will turn to three panelists. We're really excited to have three panelists joining us today to talk about emerging science and approaches to technology through, we'll hear from Matt Krause and Paul Lemieux from the US EPA Office of Research and Development, talking about different destruction technologies, and Michelle Crimi from Clarkson University. We'll then follow that up with a panel discussion. We have a few pre-identified questions, drawing from some of the questions you all submitted in your registration, and have time for an audience Q&A as well before we wrap up at 4 o'clock Eastern. And let's see, I believe the poll was available, and so hopefully you should have been able to fill that out, and if you could just show the results. So currently we have about 213 people on the webinar today, which is really exciting to have you all here, and representing a real variety of sectors as we're seeing folks putting their kind of information into the chat. We have folks representing agriculture, consulting, education, a lot of people representing government, both federal, state, and local, as well as manufacturing and a few other. So thank you all so much for being here. We're really excited to have you. Just a few quick technology reminders as we're getting started here. I know we've been on many Zoom webinars and other kind of web meetings over the past few years, but I always like to share, just a reminder to pay attention to who you're sending your chats to. We do invite you to use the chat in the webinar today to share any resources and comments. So that's the chat box here that many of you are already using. If you haven't used Zoom in a while, I know folks have different technologies that you use. You should see a kind of small black bar across your screen with a chat icon, and that's where you can click to get that chat feature. There's also the Q&A feature, which we'll use throughout the webinar as well. And so while we want you to put your kind of comments and resources and introductions into the chat box, we ask that you use the Q&A box to share any questions you have for our presenters. And we'll do our best to get to as many questions as we can during the webinar today, but given the number of people we have, we might not be able to get to all of them. And just in terms of follow-up after the webinar today, I did want to note that the session is being recorded and that will be shared, as well as the presenter slides. We'll send you should receive a follow-up email after the webinar today with those resources. In addition, we'll share the chat with everyone in attendance. That will only be the chats we're sent to everyone. So if you're sending a private chat, that wouldn't be included, as well as any questions that are answered in text from the Q&A pod. We'll also have a survey at the end of the session, and so just wanted to mention that up front and how much we would really value your feedback through the survey at the end of the event. I think that does it for introductory remarks from me. Thank you again to everyone who's introducing yourself in the webinar, and I'll go ahead and hand it back over to Rebecca to share an overview of the state of PFAS destruction technologies.
Great. Well, thank you. And as Maya said, thank you all for joining us. One quick additional note, all the slides for the presentations will be available on the AAAS EPI Center webpage. So the recording as well as all the presentations will be available for you. So as Maya said, I'm Rebecca Eicher. I'm a project director with the American Association for the Advancement of Sciences Center for Scientific Evidence in Public Issues. We'll shorten all that to say the AAAS EPI Center. We're hosting today's webinar on advances in PFAS destruction because we know there are still a lot of folks interested in learning about what the current and emerging technologies are in this space. If you want to go to the next slide. So just a quick introduction in case you're not familiar with AAAS. AAAS is a scientific membership society. So we have 170 years of being in the association world. We have about 120,000 members worldwide, and we are the publishers of the journal Science and the Science family of journals, as well as a programmatic organization. And the programs, which EPICenter is part of, all serve the mission of really science serving society. Next slide. So the EPICenter is about 4 years old. So out of 170 years, the EPICenter started about 4 years ago. And our mission is really to bring clear, concise, and actionable scientific evidence to decision makers. When we're talking about decision makers, we're thinking about local, state, regional, federal, elected officials, regulators, policymakers, decision makers, people who really need science to help them think about policies and solutions for addressing some of the most challenging issues. We know that scientific evidence is one part of the policymaking process, and we're working to ensure that folks can access and understand that scientific evidence. Next slide. So this is just a quick slide of the other colleagues that I work with at the EPICenter. And then if you have questions, you can reach out to any of us, but you'll see all of us here. We're a small but mighty force. Next slide. So we work on a lot of different topics. Today, we're here to talk about PFAS, but you can see there are other topics that we do work on and bring scientific evidence to decision makers at these different levels. Next slide. So our PFAS project, we started working on this in late 2019. And really the motivation is to engage with local, state, regional, and federal decision makers to help them understand the current and evolving scientific evidence on PFAS. We know that many different parts of this discussion and topic are really evolving quickly, and science continues to better understand things related to human health effects, contamination, treatment and remediation, disposal and destruction, which is why you all are here, and then also in risk communication. So we've been creating fact sheets, guides for local and state leaders to help them better understand the current scientific evidence, and then also doing webinars and partnering with organizations to help bring these discussions and information to the folks who really need it. Next slide. So we're not going to spend too much time introducing everyone to PFAS. We're kind of assuming that if you joined, you know a little bit about PFAS, but as a quick review, PFAS, per and polyfluoroalkyl substances, are a class of over 9,000 synthetic compounds. That number seems to continue to grow as we better understand these compounds. What really makes these a unique and interesting compound is that it is a chain of carbon and fluorine bonds with functional groups attached to them, providing them with their water, stain, and heat resistance. And that carbon-fluorine bond allows for these to be really stable compounds that are resistant to natural destruction, which is why we're here to talk about what is going on with destruction of these really complicated and stable compounds. Another challenge or set of challenges is that these are persistent, mobile, and bioaccumulating compounds. And they've been used in a wide variety of consumer products since the 1950s. And what we have found is that these compounds, which are synthetic, show up in plants, animal, air, soil, and water. So we really want to think about how is it that we can start to address these compounds and start to find solutions to removing, remediating, and eventually destroying these PFAS. Next slide. So this is just an image to give you a little more context of how we've been thinking about how PFAS cycles through the environment and highlighting some of these places where treatment and destruction really become crucial. So you can see that the PFAS are cyclic, moving from consumer goods to landfills. Within landfills, we know that landfills can release landfill leachate, and that leachate has been shown to have high concentrations of PFAS. So that's one of those places where we know we need a destruction method to deal with those concentrations. Also, we've found that the consumer goods can move into the water. So we know it's a drinking water contaminant. We know it's in our surface and groundwater. We know that it's in wastewater treatment plants. So again, this challenge of wastewater and drinking water, removing it is one step in the process, but then destroying it or actually getting rid of these carbon fluorine compounds is the real challenge. They also can be released in air emissions. So some of you may have heard of incinerating these compounds or consumer goods or pieces of material that have been coated with PFAS, but we know that some incineration or combustion of these compounds may not actually destroy all of them, and so that can be released in air emissions. There's the aqueous film forming foam that was used for firefighting. That's really ubiquitous in DoD facilities, in commercial airports. So these are all places where there are these big sources of PFAS that, yes, we could remove them from, say, drinking water, but we haven't actually done anything to break up those compounds and destroy them. So that's the real question that we're trying to work on and think about today. Next slide. So what are current disposal and destruction options for PFAS contaminated media? Per the US EPA's 2020 interim guidance, which should be updated in 2023, there were really just a few suggestions of what one can do for disposal. So there is the option to just store the PFAS contaminated material until technologies advance and we have a better understanding of what actually works to destroy these compounds. Secondly, there is the potential to use underground injection wells, but only for the liquid waste. And again, this wouldn't destroy the PFAS, it would just be a way to contain it. And then disposal in landfills. And very specifically, it would be hazardous waste landfills or solid waste landfills, because they would provide that lining and then a way to treat or an acknowledgement of treating the leachate. You may have heard of some incineration ideas. That has really been put on hold. And something that we can talk about, and I'm excited to have some of our EPA scientists here to share a little bit more of what they've been learning in that thermal space. So thinking about our emerging technologies on the next slide, it is an emerging and rapidly evolving field of research. So you can think about hydrothermal processes, electrochemical oxidation, pyrolysis and gasification, plasma, UV irradiation. And you all, I'm sure, heard just earlier this summer in August when Science published the exciting low temperature mineralization of perfluoro carboxylic acids method. And that really made a big splash in the media. And again, this is one of those spaces where it's a rapidly evolving field, and we really need to think about alternatives, what's working and what's potential. But again, thinking about what can happen now, there are still a lot of questions. So if we go to the next slide, some of these challenges. So the scale and volume of contamination in soil, water, and solid waste. And when we're talking about solid waste, you can think about some of the ways that PFAS bioaccumulate. And so we've all probably heard the stories of some of the contaminated dairy farms. Well, if the milk is contaminated, then we find that those cows are also contaminated. And what do farmers do with the cows that are contaminated with PFAS? These are all questions that we really just don't know the answers to quite yet. Another challenge is that as we start to see these emerging methods and technologies, the scalability and effectiveness of these methods really needs to be evaluated and is being evaluated by some of the folks on the webinar today. And then, of course, often comes along with the question of the cost of these technologies. But again, to think about opportunities, not just the challenges, some of our federal agencies are investing in research and development for these destruction technologies. Just to name a couple, the US EPA and the Department of Defense have invested, and there are industry and academic researchers working to develop new destruction methods. So it is an exciting and evolving field, and that's why we wanted to be here today to talk about what's out there right now and what's kind of emerging and what can we start to look for in some of these technologies. So I think I will now let you all hear from our panelists, which is very exciting. We have Max Krause, we have Paul Lemieux, and we have Michelle Crimmy here to really share about their knowledge and expertise in this destruction space. So with that, I'll pass it over to you, Maya, and welcome our panelists. We're thrilled to have you.
Great, thank you so much, Rebecca. I think that was a really helpful overview. I know it sparked some thinking in me and questions, and I look forward to hearing from our presenters and thinking more about kind of the destruction opportunities, questions, and areas of research. So we'll start off with a presentation from Max Krause from the EPA. So Max, I invite you to turn on your video and start sharing your screen while I introduce you. But just as briefly, Max earned his PhD in environmental engineering from the University of Florida in 2016 and has been with the US EPA's Office of Research and Development for 6 years, where he researches solid and hazardous waste management with a focus on landfill emissions, waste characterization, and PFAS treatment. And Max in his presentation is going to talk a bit about destruction methods, including supercritical water oxidation and electrochemical oxidation. So I can see your slides on the screen, Max, so that looks great. And just a reminder for folks as you're listening to the presentations, if you do have questions, go ahead and use that Q&A pod at the top or bottom of your screen, depending on how your Zoom is set up, to enter your questions, and we'll talk about those later in the session. Great. All right, Max, over to you. Thank you.
All right, thank you, Maya, and thanks, Rebecca, for the introduction to the topic. Again, my name is Max Krause. Me and my colleague Paul will talk about some of EPA's recent work on PFAS destruction and the ongoing research that we have here in the Office of Research and Development. Let's see if I can get this going here. All right, so I did want to give a quick introduction for those that might not be familiar with EPA's Office of Research and Development, or ORD as we call it. ORD is not part of, is an independent, or is the scientific branch of EPA. So we are not part of the policy folks in DC, and whereas enforcement and compliance is distributed among 10 regions within the EPA, which on this map are kind of color coded by the states. We have offices, ORD offices, labs, spread geographically around the country to meet the different state or geographic needs with regards to kind of specific research. But we do collaborate across the country. And so I'm located in Cincinnati, Ohio. Paul is located in Research Triangle Park in North Carolina. But we are collaborative partners and in research and in kind of the work that we do here, both in waste management and in PFAS. And so I kind of wanted to frame this. I think this is pretty familiar with most folks, but there's a large data gap for understanding, the fate of PFAS within the wastes and kind of within the infrastructure, the waste management systems that we have. And so the idea is to, we can characterize things, but we also want to understand technologies for effective destruction of the actual chemicals that we're concerned about. And so it's not just understanding how can we safely dispose of them, but how can we kind of break these carbon-fluorine bonds. We have recently scoped out for EPA, ORD has recently scoped out our research action plan, and that's something that you could search online for, which kind of presents the priorities of PFAS and all research within the Office of Research and Development. And so you'll see the types of products, and by products, I mean deliverables, research areas that we have scoped out for the next 4 or 5 fiscal years, so up through 26. And so you will see identification of research areas, behavior, destruction effectiveness in different types of wastewaters and biosolids. And so that should give you an understanding that this is something that we are continuing to work on and is a high priority for the agency for the foreseeable future. Rebecca showed a very similar slide to this, and like she said, we're not going to focus really on anything. I'll assume that you had a PFAS 101 type of course already. And so the idea here is that we are focusing in multimedia environments, looking at soil, water, and air. We're trying to understand what technologies are applicable in different cases, because PFAS are kind of ubiquitous. We see them in our blood, in our wastewaters, in our drinking waters. And we're trying to understand when and where technologies are appropriate for either the removal or the destruction. And so, again, Rebecca kind of set the stage here. Combustion has been an existing waste disposal or waste destructive method. And so there's some concern about how effective it is for PFAS, primarily for liquid wastes. Combustion does not seem like the right tact or the right technology application for these things. And so, especially when we're talking about aqueous film forming foam, or AFFF, something that's very high concentration in PFAS, the idea that you would incinerate it gives some concern to how effective that would be. On the other side, where we have wastewater sludges or landfill leachates, where the concentrations of PFAS might be higher than, say, drinking water sources, but relatively low compared to AFFF, but the volumes of liquid waste are substantially higher. And so again, there's a break between, maybe low concentrations, but large volumes, and then wastes like AFFF, which are relatively low concentrations of material, but very high concentrations of PFAS within that material. And so we're looking at, what I will do is talk about some of the destructive technologies that we've looked at specifically for liquid wastes, and then I'll hand it over to Paul, and Paul will talk about the conventional combustion systems that are looking at generally solid materials. So when we look at liquid waste destructions, not just within the agency, but across the academic list, or the academic consortia, you'd see hundreds of articles, especially recently, regarding different types of technologies that can be used to destroy PFAS. And the idea, of course, is some of these things we're doing at different scales, at bench scale, maybe a development scale. And so a few years ago, especially during COVID, we convened a group of different researchers within ORD to kind of do a sniff test on some of these things and understand where do we think these things have legs. And so again, kind of looking throughout the peer-reviewed literature, we see a lot of things probably can walk, so to speak, with technology, things that look promising, but can they run? And can they be scaled up? Can they reach commercial maturity so that these could actually be deployed for waste treatment systems for the long haul? And so we don't have a ton of time today, so I'm not going to run down the entire list. What I am going to focus on today are the hydrothermal processes. So that's that first bullet there. And then the second bullet, I'll briefly mention electrochemical oxidation. I will also briefly mention pyrolysis, which isn't shown here because that's kind of more, that technology already exists, although it's not very common in the United States. It's much more common in Asia. So I'll mention one of the projects that we did. So I'll mention a couple of things about supercritical water oxidation and hydrothermal processes. I'll mention something briefly about electrochemical oxidation and how we've collaborated with some folks to understand that technology. And then I'll wrap it up with a discussion on pyrolysis and biosolids. So hydrothermal technologies, this is essentially pressure cooking of water or wastewater. What you're doing is you're heating a reactor and pressurizing it. You're adding a gas to pressurize the system, so it's not just the boiling of water or the heating of water. It's a contained system, so the water achieves temperatures higher than boiling, and the idea is that we're crossing what is known as the supercritical line, the supercritical point. The idea is pressure is 22 megapascals, which is really not that high. It's a little more than 3,000 psi. And then the temperature is 374 degrees Celsius. The conditions allow for water to inherit some of the unique properties that it has in its gas phase. So just like plasma is kind of this fourth state of matter, not liquid, not solid, supercritical water is not liquid or gas, it's something in between. And so it has different properties, and those properties make it very useful for breaking of organic bonds. And so SQO, or supercritical water oxidation, has been used, or was developed in the 80s for the destruction of chemical warfare agents, PCBs, PAHs, and halogenated compounds, which are compounds that have chlorine or fluorine on them. And so there was already some existing literature that suggested this technology was going to be applicable to PFAS contaminated wastes. The idea here again is that you're pressure cooking a material. There's like a recipe for this, which is kind of what you see at the bottom there, where you have to add some oxidants. You add a couple things to the system to make the magic happen, but the end products ideally are water, it's the sodium fluoride, so that results from the carbon and the fluorine in the PFAS breaking apart. So the fluoride would go to this salt and become a sodium fluoride, and then the carbon becomes carbon dioxide and is emitted to the atmosphere, and then you have salt precipitates that are formed, and that's kind of a waste product. The idea here is that we're running these temperatures at much lower than typical combustion temperatures, and so unlike a combustion unit, you would not see SOx or NOx generation. But there are still a lot of unknowns with this technology, and I'll go through those here. So again, a couple of years ago, at this point, back in 2020, we'd partnered with 4 different SQO vendors, and again, this technology has already existed for different applications, and so the technology has already been developed. They've kind of the different vendors already exist and have experience in either making stationary or mobile platforms. And so what you see here are 2 pictures. One's from Aquarden, which is a company in Denmark. And then the lower picture below that is some mobilized kind of tractor trailer units from General Atomics. And so what we did was we ran 4 independent tests. We didn't really give too much direction other than we told them, we're sending you a sample of AFFF, which contains PFOA, PFOS, and we'd like you to treat this waste. We conducted the targeted analysis before and after, oversaw it so that we would have some understanding that the characterization of what went into the material or what went into the system, what came out of it. And then for only in this final test with General Atomics, we did some gas phase analysis. And that was because this test was conducted later, or I should say, in 2020, later in 2021. And we're still just kind of developing a lot of these methods, especially on the gas phase side. Targeted analysis, where you're looking at 20, 24, even 40 compounds of different PFAS, has been really well developed for drinking water, but it is much harder to do for really complex wastewaters, things that have a lot of other co-contaminants in them. And it's even harder for gas phase analysis, where you have to take an absorbent or some other material and then do an extraction off of that. And so we're kind of learning as we go, both with methods and analysis. But what we, I'll show these in the next couple of slides, but what we showed was that, and what we saw was that we saw greater than 99% reduction of our targeted PFAS in each of these case studies. And so we became pretty confident, again, that this gave us some indication that this was not a one-off, or that there wasn't somebody that was doing something so unique, that the technology itself has the potential to effectively reduce or destroy PFAS. And so what we saw here with, I'll just give you a couple of the comparative tables, and this is not meant to be a direct comparison across vendors. This is really just meant to show you the kind of range of chemicals and parameters and concentrations. So again, we didn't tell them what concentrations to start with, how dilute the sample, to make your sample. We just wanted them to run it through their system, evaluate it kind of as they would, and kind of work to understand the material. And so I'll note here that the concentrations here are on the log scale. And so each step up or down is an order of magnitude 10 times. And so the reduction from something like, and again, this is AFFF, so it's far higher concentrations than you would see in drinking water, but something on the order of 40,000 parts per billion, or 4 parts per million. or 40 parts per million. So that reduces down to about 100 or 200 parts per billion on the total summation of PFAS that we analyzed. And what we saw was really great destruction, kind of to non-detects for the carboxylic acids. We saw some resistance in the sulfonic acids. And this was fairly consistent across these different groups. But what we think, and after the communications between these different groups as well, is that changing residence times or kind of recycling through the systems would reach a level. And so I'll mention again, or I'll mention all this as well, is that this is wastewater, and it wouldn't necessarily be held to the standard of a health advisory limit for drinking water. And so we weren't targeting any specific value on the back end for what we wanted our treatment, result to be. But I know that question will come up, and you'll see these numbers as reductions. It doesn't go to zero, or it doesn't go away. But again, the idea here is, in a first assessment of the technology, do we see significant reductions, and do we see, importantly, reductions across different types of compounds? So again, do we see carboxylic reductions and sulfonics? For those that might not be so familiar, the idea is that for PFAS, with all these different types of compounds, they have very unique behavior, and I'm trying not to make it too complicated, but those functional groups, so when it runs through a system and it is broken apart, it doesn't really break apart at the middle of the backbone. It breaks apart at the functional group at the end. And so it's very possible that the functional group can go away, and so you lose perhaps the PFOS, but it can still become a different type of PFAS because it still has 6 carbons, 5 carbons, 4 carbons. It kind of has to break down sequentially. And so the question is, you see some things that are have increased. For example, here, this PFDA has increased. There's question of reformation or formation, and there are a lot of questions to be answered from these first studies, but we, again, feel pretty positive. So again, just giving you a sense of the starting points and the ending points, and kind of what we saw and kind of what makes us excited. I think the other thing that we were interested to understand is what other parameters to look for when we look at these technologies. Certainly when we're trying to understand something like hydrothermal processes, where you're creating a lot of acid and adding neutralizing buffers to prevent hydrofluoric acid formation and get it to form salts. So you see the influent pH is very basic. The effluent pH is very acidic. We see chemical oxygen demand significantly decrease, which again gives you an indication of organic activity or chemical activity in a wastewater. And then finally, something that is very helpful for us that we find is a simple fluoride analysis, and fluoride is done through ion chromatography or ion selective electrodes. And so when we see that far right figure shows the total amount of fluoride or fluorine that we look at on the influent. And so when we measure with fluorine based on our targeted analysis, and then we look at our effluent, we see significantly more fluoride. So significant generation of fluoride, more than we can account for with our targeted analysis, which suggests that SQO is destroying PFAS that we cannot even target at this point, which again, it highlights the fact that it's able to destroy or reduce these concentrations for multiple types of PFAS, again, things that we are not even looking for at this point. So again, I kind of wanted to back up here and say that hydrothermal research is pretty exciting for us. It's called a lot of things, so depending on the different research areas, you might see it as hydrothermal alkaline research, or hydrothermal alkaline treatment, hydrothermal liquefaction, hydrothermal processing, and then supercritical water oxidation, which I'll say might be the cousin to the other three, but is the idea here is the same, is that you're using pressure and temperature to cook out this PFAS. And across the different publications, not just within EPA, but outside in other academic circles, is that we see very high destruction efficiencies, high defluorination, low treatment times on the order of seconds to minutes, which kind of, again, pushes us to this idea of, okay, you could treat gallons, you get a system going with gallons per minute, hundreds, thousands, so that it's something that seems like it could be viable for the future.
And next, I just wanted to, jump in and just say just a few minutes here, and then we transition.
Sure. So again, I wanted to push pretty hard on hydrothermal because we had that work out there and done. I'm wrapping up a report here on electrochemical oxidation, and so I don't have as much information to share with you here today on this. The work was done in collaboration with AECOM on their defluoro system, and they had a lab scale demonstration here, and so this is just a picture of that. In a similar way, we've looked at the analysis of targeted PFAS, total organofluorine, fluoride, chemical oxygen demand, and that work is forthcoming. We're still putting together the final pieces on that report, likely early 2023. And then I will say again, pyrolysis is an interesting thing, interesting technology that we have evaluated, and the research has been completed on this project. This is an operating unit that is located in Redlands, California, outside of San Francisco. The system was identified. It was not chosen because, the pyrolysis system is treating a sludge and creating a biochar. And we found and collaborated with this group, not because that the system was known to be impacted by PFAS or the wastewater was known to be impacted, but the technology was there, and it's a unique technology and something that's promising because the temperatures, the operational temperatures inside are quite high. And so something that we found was, we went and we sampled and we did see PFAS within the wastewater, but that the produced biochar, the material that ran through the system did not have detectable levels of PFAS. And so that research also has been published, and we can share that with you as well. I kind of wanted to give you a sense of where we think these things are at. So this is a chart about technology readiness. We have electrochemical oxidation, supercritical water oxidation, pyrolysis with different waste streams. And again, these are currently being analyzed. EPA has now expanded SQO to look at biosolids, to look at landfill leachate. And so we are currently investigating these other types of waste streams and their applicability with these different technologies. But with SQO and with pyrolysis, we see these units already being sold and already on the market, in place. And so there is some excitement or some reason to be happy here. I think electrochemical oxidation, there are some development pilot systems coming online, and we're eagerly awaiting the results of those analyses. So I'm going to hand this over to Paul. I don't know if he'd like to share his screen or go off mine, but we're going to move over to thermal treatment systems, combustion.
Great, thank you so much, Max. Really appreciate that walk through those particular technologies. And Paul, as you're pulling up your screen, or I'll go ahead and just as a brief by way of introduction, Paul Lemieux is a senior research engineer, also at EPA ORD, and he's in the Homeland Security Materials Management Division of the Center for Environmental Solutions and Emergency Response. Paul's been with the ORD for 35 years, and since 2002, his focus has been on the management of waste from cleanup after chemical, biological, or radiological incidents, as well as foreign animal disease outbreaks. And as a part of this work, he's been also working on developing decision support tools to aid decision makers during these types of incidents. And then more recently, he's been back working with his combustion research colleagues investigating thermal destruction of PFAS. And I see you've got your screen share up. So look forward to hearing from you, Paul. And just, I see a few questions have come in the chat and in the Q&A. And just as a reminder, if you can use the Q&A tool to input your questions, we'll use that as our source when we go back for the Q&A later in the session. Thanks, Paul.
Thanks, Maya. Can everybody see the slides?
Yes.
Okay, so now this is referring mostly, the next part of the presentation is going to be referring mostly to conventional thermal treatment and some of the challenges and some of the things that we found in our research. From a chemistry standpoint, the chemistry of PFAS destruction is fascinating. It's different than anything we've seen before. We had they did a lot of work on dioxins in the 90s and the late 80s, and this is one of those type of things where the chemistry is very unique, and so it's probably going to lead to unique approaches for establishing operating regimes for processes that manage PFAS. So again, the highly electronegative fluorine makes the CF bonds particularly strong, requiring very high temperatures for destruction. Carbon tetrafluoride is probably the worst actor in this group of chemicals. It requires about 1400 plus degrees C in order to achieve 4 nines of destruction. One of the things that the EPA's regulatory offices are interested in from a PFAS destruction standpoint is how do they establish operating parameters for facilities that are burning PFAS. Currently, for example, hazardous waste incinerators will have like a carbon monoxide limit, or maybe they'll have a hydrocarbon limit, and that does not appear to be sufficient for dealing with the PFAS. One of the things that we found in our initial experiments is the functional group that's at the end of the PFAS is relatively easy to strip off at high temperatures. The problem is that remaining carbon fluorine structure that's left, that's extremely difficult to destroy all the way down to sodium fluoride and carbon dioxide. And so you have a bunch of free radicals floating around where the functional group was stripped off, and those remnants might react with each other in order to form different molecules. So somehow the products of incomplete combustion and the intermediate chemicals that you see as these things degrade are going to be an important part of the approach that's going to be taken to hopefully establish operating parameters for facilities. One of the things we're lacking is field data. It's very difficult to get out and do field tests anyway, and just because of the politics of PFAS and the concern that different the communities may have and the facilities have, it's been difficult to get out and do field tests. And the PICs are very important, the products of incomplete combustion. So we have to take that into account when we assess the destructibility. And as Max had mentioned, the sampling and analytical methods for combustion devices are nowhere near as far along as the sampling and analytical methods are for the water and drinking water and wastewater side of things. So at the same time we're doing experiments looking at the destructibility of these compounds, we're also doing experiments to develop the emission sampling and analytical methods that would be used out in the field and in the for regulatory purposes. So we've done some experiments on bench scale incineration of wastewater sludge, looking at 10 PFAS compounds of various carbon chain length based on the NIST domestic sludge reference material. And we were able to get good destruction efficiencies. But again, the key element is what are the byproducts that might be left over after you get your destruction. Another particular problem that we seem to be having with the experiments burning PFAS is that we can't close the fluorine mass balance. A lot of the combustion devices out there have refractory walls that are made out of silica, and the HF reacts with the silica. And so after you shut off the PFAS feed, it takes a while to go back down to 0 HF because it's been reacting with the reactor walls and has to come off there. So it's very difficult to close a fluorine mass balance. For these studies, we found that the majority of the recovered PFAS was found in the residual char. Additional work needs to occur on this topic. We've done a look at incinerating wastewater sludge. We did some tests at a multiple hearth furnace using non-targeted analysis, which that's one of the main challenges on the analytical side. Is there, you can do targeted analysis and look for 20 or 30 PFAS compounds that are well known to exist, but there's not a lot of knowledge of the greater number of PFAS compounds, which runs in the thousands, that might be important from a incinerator characterization standpoint. And so you end up having to use non-targeted analysis, which for those of you who have been doing work with GC mass spec, usually they're called tentatively identified compounds. And so there's a rich number of tentatively identified compounds that we have to establish whether we have a good method to quantify them and how important they are, both from a health effects standpoint and from a incinerator monitoring standpoint. So all of the time we're doing the experiments looking at incineration, we're also looking at the methods development as well. Another key waste stream is the activated carbon that is used to in water treatment facilities for PFAS removal. But then you have a large waste stream of activated carbon that you need to maybe regenerate and reuse, or you can dispose of it through technology like incineration. So there's currently some work going on at North Carolina State University in conjunction with CERTA to look at the bench scale, to look at destruction of granular activated carbon and potential regeneration. The pilot study is complete. We're waiting on the results. We're hopefully going to be able to find some partners that we could go out in the field and evaluate some of these activities at the full scale. You'll see that as a common theme throughout this is we've been able to do experiments at the bench and pilot scale, but being able to get out in the field is an important part of being able to provide the user community with information on how they might be able to manage these compounds. Cement kilns are a technology that look very promising. We'd love to be able to get out and do some field sampling. One of the advantages that cement kilns have is that there's parts of the furnace that are up to 2000 degrees C, so they're hot enough to decompose even the most stubborn PFAS compounds. And the presence of a lot of calcium in the cement kiln can promote the formation of calcium fluoride and essentially remove the fluorine from the gas phase. So it looks like it would be a technology that would be very promising for this. We would love to get out and do a field test at a cement kiln. Some of the experiments involve looking at different analytical techniques and different measurement techniques in order to both evaluate our experiments as well as to look at things that could be brought to bear out in the field to monitor commercial processes that are processing PFAS. So we use a thermogravimetric analysis combined with GCMS, and we can look at some of the thermal stability issues of some of the PFAS variants and their salts. We can program different temperatures in. And so it's an effort to look at some of the products of incomplete combustion from destroying the PFAS compounds that shows a lot of promise. One of the experiments that I'm personally involved in is in our Research Triangle Park facility. We have what we call the rainbow furnace, which you can kind of see why it has different colored sections. And this is a 85 kilowatt small pilot scale incinerator. And we've been working on it, looking at injection of C1 and C2 PFAS compounds, which are gas phase, looking at where can we inject it, what temperatures, what residence times affect the destruction. And we're combining this with a numerical model of incinerating PFAS that is showing a lot of promise that we'll be able to hopefully predict our byproducts and major products numerically and compare it to the data. And it shows a lot of promise as being able to predict many of the original compounds as well as some of the picks. And it'll help us understand the mechanisms of their destruction. The other thing that I have to mention is that FTIR has come a long way in the last 10 years. It used to be really kind of a crappy method for measuring combustion sources because you had trouble separating compounds that absorb in the infrared like CO and CO2. You can't really separate them very well. But now we have these powerful digital signal processing microprocessors, and FTIR is fantastic. We can measure a number of the fluorinated species, a number of the non-fluorinated species, and normally you would have to have a separate gas analyzer for many of these, but we can get, for example, water vapor and carbon dioxide and carbon monoxide all at the same time. And we can measure the original compound as well as many of the products of incomplete combustion as well. And this is all in real time. So here's an example FTIR trace where we're in real time measuring compounds that span many orders of magnitude in concentration. And based on some comparisons with conventional sampling methods, for many of the compounds, FTIR does a really good job at analyzing it. So that's one of our main tools that we're using right now for doing these experiments. And this is where we notice that HF doesn't immediately return to baseline after we stop the PFAS feed. It takes quite a while to come back to zero. The modeling is very interesting. It's the company Reaction Engineering and International. They had done a project for the Department of Defense back in the early aughts to look at the operation of the chemical warfare agent incinerators at the Tooele Army Depot. And they came up with a scheme for doing full three-dimensional reacting flow, but you don't need a supercomputer to do it. And so we have since adapted their model to work on both chemical warfare agents for building materials, looking at if somebody was to contaminate a house with chemical warfare agents, which has actually happened over the last several years. But we have added the chemical destruction mechanism for PFAS that NIST developed back in the 90s when they were looking at alternate refrigerants to minimize the impact on the ozone layer. So they have a reaction set that has over 1,000 reactions that look at C1, C2, and some of the C3 destruction. And we're currently adding the functionality to do the same thing for the larger molecular weight PFAS compounds. EPA has also been working on a PFAS thermal treatment database as a publicly available database that has all of the scientific literature that we've been able to come across for different aspects of PFAS destruction, so that hopefully you don't have to go hitting, page 10 of a Google search to find the things that are important. And this is available publicly, the URLs at the bottom of the page. And here's a number of references that we have found or written ourselves or whatever, but and then there's some helpful resources on the EPA's webpage that hopefully will give you some of the information that you might need as you look into making some of the plans for how you might get rid of these materials in a safe way. And I think we also wanted to acknowledge our colleagues. This is a truly interdisciplinary research team of people that look at air emissions, that look at detection limits, that look at different detection approaches, that are water people, air people. It's become obvious that dealing with the PFAS problem is going to take a lot of different scientific disciplines in order to really make a dent in the problem. So it's very much an interdisciplinary bunch of people that we have working on this. And I think that was my last slide, so I will turn it back over to Maya.
Great, thank you so much. Fascinating to hear about all these different types of thermal treatments and some of the questions. And I really, just through my work in this space, have your last point about how it's such an interdisciplinary challenge and takes so many different people working on different types of, with different expertise to come together is really resonates. So I do want to now transition to our final presenter, Michelle Crimmy. And as I'm doing that, just a request maybe for Paul and Max as you're listening in. There are a few kind of clarifying questions that are about different details that came up in your presentation in the Q&A box. And if Paul and Max, as you're looking at those, perhaps you could type the answers to a few of those questions that are pretty detailed. So Michelle, thank you for turning on your video. So thank you so much for being here. And just by way of brief introduction, you're the co-founder of REMWELL, and you serve as the Dean of the Graduate School at Clarkson University. And your research focuses on developing in situ treatment technologies for groundwater contamination and determining the impact of groundwater technologies on aquifer quality and integrating treatment technologies for optimized risk reduction. So there's a lot more, and we've got full bios or longer bios for each of our presenters on the Epicenter's website for this event. So with that, I'll turn it over to you and look forward to hearing your presentation. Thanks.
Great, thank you so much, Maya. Just confirming you can see my title slide, and hopefully we advance in the correct
I can.
way. Awesome. Well, good afternoon, everyone. I really appreciate the opportunity to talk to you today, and I'll be introducing two additional emerging approaches for destructive treatment of PFAS, focusing on Sonolysis and on plasma treatment, as well as on the use of treatment trains for efficient treatment of PFAS. So, you've heard our other speakers today talk about how challenging PFAS are to treat because of the carbon-fluorine bond, but there's a couple of other chemical properties that are really at play here that make them so difficult to treat. One is they are surface active, and because of that, they behave differently than other typical contaminants on which we built an entire history of remediation upon. They also don't partition that well into other media. So partitioning is an approach that numerous treatment approaches rely upon. For example, stripping contaminants out of water in the ground into air to capture above ground, or transferring PFAS from water onto a disruptive media like activated carbon. I mean, it works, but they don't partition quite as well as some of the other contaminants we've worked with historically. Furthermore, PFAS are typically present in mixtures of a broad array of PFAS compounds, as well as other co-contaminants. And these have a wide range of properties, making it difficult or really nearly impossible to find a single solution for these broad mixtures. And further yet, PFAS precursors, or some of the larger PFAS compounds, can actually turn into the compounds of concern through either natural processes or through the treatment processes that we're actively using to manage these target compounds. So, tricky problem. To treat any contaminant in groundwater and drinking water, we have 3 big picture options, and Rebecca talked a little bit about these this morning. We can immobilize, keeping them in place. If we're talking about a groundwater subsurface system, though, the downside is they're still there. There's questions about the long-term effectiveness of immobilization approaches. We can separate them. We can remove them from water, concentrate them onto adsorbents or other separation processes. But now we have clean water, but we still have a concentrated waste stream to manage. Or we can destroy them. The focus today, breaking PFAS down into harmless products. And we've been using these different approaches for other contaminants for many years now. But as I mentioned, PFAS present some unique challenges that call for a transformed or for novel approaches, or at least some twists. So one twist that we look at is to combine treatment approaches that focus first on concentrating PFAS to cost effectively reduce the mass or the volume to which our more expensive and energy intensive destructive treatment approaches are then applied. So currently, most available solutions for the ultimate management of PFAS all take them offsite, whether we're talking about landfilling or incinerating soil sorbents or other media. But we and many others are working on solutions that can operate fully on site toward more sustainable solutions that can help eliminate moving PFAS around in media, or around in the environment, or to different locations offsite. To date, most approaches to manage PFAS in groundwater systems operate ex situ, or above ground, which means pumping large volumes of water out of the ground to treat above ground. So we're also working on some in situ approaches that will treat PFAS in groundwater underground directly where the contamination occurs. And this can eliminate expensive and energy intensive pumping. So the 2 approaches I'm going to focus on going forward here are both destructive treatment solutions designed for operation on site. These include sonolytic treatment and plasma treatment, as I mentioned earlier. And I'm focusing on these particular approaches because they're 2 of several that we're working on here at Clarkson University. So, selfishly speaking, these are the 2 that are easiest for me to talk about. It doesn't mean that I'm trying to imply that they're the only 2 approaches out there, or even the best 2 approaches. One thing that we've learned through our history of managing contaminated sites is that there are no silver bullet approaches. Different site conditions are going to call for different solutions. And the first one that I'll talk about here is an in situ sonolytic treatment approach. So what is Sonolysis? Sound waves in the ultrasound range create cavities in liquid, and these cavities look like bubbles. And because many PFAS compounds are surface active in nature, they line right up on the interface of the bubbles. But once the cavities reach a critical size, just like bubbles, they'll collapse. And this results in extreme heat and pressure at a micro scale. And that basically tears apart the PFAS molecules. We've developed a sonolytic reactor at Clarkson. And the idea is that it gets placed within a horizontal well in the subsurface. Horizontal wells passively capture water. They're a path of least resistance for water to flow in the subsurface. So a well that's even less than a foot in diameter can capture water at a treatment zone up to 50 feet or more underground, requiring no pumping of water at all above ground for treatment. So the idea is that water flows into the reactor, it's treated by Sonolysis in the reactor, and then clean water exits the well. So we've tested the reactor in the lab using actual field contaminated groundwater. We apply Sonolysis to the samples, and then we analyze for PFAS compounds, for smaller chain byproducts, and for those larger precursors over time. And these data help us understand, the necessary field scale design conditions like retention time in the well that will be necessary for it to work at the field scale. So here you see example results for 3 different field sites, and each is represented by a different color. And this particular figure focuses on PFOA, the left-hand bar for each color, and PFAS, the right-hand bar. And you can see that 90% treatment is achievable, and this was even before the reactor has been optimized, and we continue to work on that optimization. I mentioned that we measure other key compounds. In this graph, you see changes in concentration over time. These are normalized, so a value above 1 on the y-axis here indicates that the compounds are being formed during treatment, concentrations above their initial levels. But then we see these intermediates, whether large precursors or the shorter chain compounds, they'll increase in concentration, and then they decrease as they too are ultimately destroyed along with the PFOA and the PFAS. We have an upcoming field demonstration of this in situ reactor. It's funded by ESTCP in partnership with Arcadis, the Army Corps of Engineer Research and Development Lab, or ERDIC, and Ellingson DTD. And this is going to take place in a horizontal well that's already actually in place at Peterson Air Force Base in Colorado. So the bottom picture here shows you a cross section of that well. And early next year, we're going to be popping our reactor into that well, turning it on, and validating its operation in the field. So keep your fingers crossed for us, if you would. All right, moving quickly on to destructive treatment of PFAS using plasma. My colleagues Tom Holson and Selma Medetovic here at Clarkson have designed, built, and tested a plasma treatment system, which they're now commercializing under their company DMAX Plasma. Plasma treatment uses electricity to convert water into a mixture of highly reactive species, and a key one of these is aqueous electrons, and these are very aggressive reactants capable of destroying even the most recalcitrant PFAS compounds. It also happens to be a process and a system that's very cool to see in action, as maybe you can tell even a little bit from the photos here. I get a little bit jealous because when people come to visit our labs here at Clarkson, they always want to see the plasma reactor. There's not much to see with sound waves that you're trying to implement underground, but it is cool. So let's see, Tom and Selma and their research team have built different scales of reactors that you see here in the schematics. And the one on the top right is their deployable field scale unit. And about 3 years ago now, seems hardly possible that much time has passed, but Tom and Selma and their team, along with GSI Environmental, performed a field demonstration at Wright-Patterson Air Force Base. And here in the tables and in the graphs, you can see the initial and the final concentrations of key compounds, including our typical targets, PFOA and PFAS. And you see effective treatment of all of these compounds, besides these little 4 carbon chain compounds, PFBA and PFBS. So Tom and Selma, and they're students in the lab mostly, they got to work on some approaches to enhance treatment of these short chain compounds. So plasma reactions occur at the water surface, at the interface with air. And those smaller 4 carbon compounds, they're really soluble. They need a little help getting to that interface. So the cationic surfactant CTAB is one that can actually help them get there. So look at the difference here with PFBS, one of those 4 carbon compounds, with and without that surfactant CTAB. So plasma works effectively, even for some of these really challenging to treat compounds. moving a little quickly, but one wheelhouse for plasma treatment is part of a treatment train, like I mentioned at the beginning, where really low concentrations of PFAS can be concentrated out of large volumes of water into a smaller volume. And then those small volumes of concentrated PFAS can be destroyed by plasma. So the example you see here is an initial separation by ion exchange. You can see some of the equipment by project partners, ECT and Wood here. Once the resin is spent, we can then get the PFAS back off the resin for destructive treatment, using different mixtures of chemical solutions that can overcome both the hydrophobic and hydrophilic interactions of the PFAS with that resin. So we can pop them back off the resin. And then, we can even reuse some of those resin regenerants, but then we have this highly concentrated still bottoms. Here, initial concentrations are in the milligram per liter range. So we moved them from parts per trillion in large volumes down to really low volumes of these milligram per liter concentrations. And you can see here, very effective treatment of these larger chain and our target compounds here in these two figures. And here you see the smaller chain compounds. And again, the addition of CTAB here at the red line time point really helps to get these smaller chain compounds. So wrapping up, you've seen several examples today of destructive treatment technologies for PFAS. The question that we get all the time is what's going to push some of these forward to market? How do we know who the winners are going to be? And, some of the key considerations are listed here, and you heard the other speakers refer to at least some of these. And one is the ability to validate that these approaches are fully destroying PFAS through fluoride recovery, through detection of intermediates and byproducts, through advanced analytical methods. We need to make sure we can understand the impact of co-contaminants and precursors on treatment. Energy cost, I think, is going to be a big consideration, one of the key drivers for what's going to emerge, as well as implementation challenges. You probably hear a lot about challenges with scaling up some of these technologies, but it's not just scale up. There's also health and safety concerns and how they would get implemented on a site in a particular set and setting. And there's still a lot to overcome. So as we feel hopeful with the emergence of many of these technologies, we remain cautiously hopeful as we work through some of these key challenges. So I apologize for talking a little fast. Wanted to make sure we save enough time for the Q&A, but thank you so much. And I will stop here. Thanks.
Thank you so much, Michelle. Really, and to all of our speakers, it's such a complex, complicated topic with a lot of different aspects. So I really appreciate you walking through those different technologies and framing up some of the kind of challenges and opportunities. So I want to invite Max and Paul to turn your cameras back on here, and we'll have a little bit of a time for a panel discussion and Q&A. Thank you. I know a number of the questions that came up in the Q&A pod during your presentations you addressed, which is great because they're some of them are very technical and maybe pretty specific to certain situations. And so as we're reflecting on, as we're reflecting on the different presentations and the different challenges that folks are facing, we know, like, for example, in looking at the responses that many of our the participants in the webinar are on today, we know that many folks who are struggling or wrestling with PFAS contamination and thinking about the best approach for in their communities, or they're dealing with different contaminated media. We saw those diagrams earlier that had kind of the various places and ways that PFAS appears in the environment. And so, Paul, I'm wondering if you could share a little bit, just kind of reflecting on how the different types of contaminated media affects kind of the appropriateness or efficacy of different destruction techniques as people are kind of thinking about the different options that are out there.
Well, our experiments so far have only involved burning gaseous compounds, the C1 and C2s, and we've burned some light water, which is one of the AAAF formulations. And we have not done any of our experiments on solid materials yet. We have another pilot scale combustor that's a rotary kiln, and we're trying to get it geared up to do those experiments to look at some of the issues like, maybe not regeneration of GAC, but just destruction of it, that might have PFAS in it, or anion exchange resins, or some of those type of solids. And we'd like to be able to do some experiments in the rotary kiln to look at that, because when a lot of commercial facilities feeding these materials in continuously is difficult. And if they're declared hazardous pollutants by EPA under CERCLA, that may complicate doing, continuous feeding even more, because facilities may have to take the material as they receive it and feed it into their processing unit as they feed it. So, for example, if you get a barrel of activated carbon that has PFAS in it, they may have to feed the whole barrel into the incinerator just to prevent workers from being exposed to some of the compounds that might be there. And that results in transient formation inside the furnace, as the oxygen might be locally depleted and may take a few minutes to come back. So that's one of the things we're very interested in is, what do we do with those particular waste streams? And as we look at all of this universe of available technologies, there may be certain ones that are much better for certain of the waste streams. And we don't know yet, but like supercritical water oxidation, that looks like that would be very effective for purely a liquid waste stream. It probably wouldn't be something you'd want to use for a solid stream or biosolids, but who knows what they might be able to do to alter the way the mechanism works to feed something different. But conventional incineration can handle all sorts of different types of media, but it may not be the optimal technology for certain types of media. So that's one of the things that we're looking at.
Thanks. Michelle or Paul, do you have anything to add to that that comment? Thank you. Well, Michelle, I know you talked about some emerging technologies, and we heard from Paul and Max about other types. And I just wanted to, we know that there's a ton of research happening, a lot of kind of exciting developments every day. Are there any other big emerging technologies that we didn't get a chance to focus on during this set of presentations that are standing out to you as things that are promising?
Sure. Rebecca mentioned at the beginning, I think it was Rebecca, maybe it was you, Maya, but the new approach that has emerged from Northwestern, I think that's intriguing because of the fact that it is a low energy approach. One of my colleagues here at Clarkson's has started working on ball milling, and that's funny because I just peeked at the chat and see something in there about ball milling. So and I think that's actually showing some interesting promise. It was, I remember back in the early 2000s, maybe there was interest in ball milling for VOCs. And I think it just ended up not being as efficient as some other approaches for VOCs. So it kind of didn't get a whole lot of attention, even though it was effective. But because so many of these destructive approaches for PFAS really are energy intensive and costly, I think it has a potentially new place to emerge in the market. So I'm interested to see what comes out of some of that work.
And for other folks on the webinar who might be like me and not really familiar with what ball milling is, could you describe that process?
Yes, and actually, I think Paul just popped a good description into the chat. It's really a mechanical process, sometimes with chemicals, sometimes without. But usually the chemicals are there to kind of help the process along. It's almost like you can think about it like grinding, and just like Sonolysis has these really micro scale effects where it's extreme temperature and pressure, but not something you would measure at the macro scale. I think the same is true of ball milling. You get these really massive impact and high pressure situations that can create these same kinds of free radicals that will destroy the compounds as well as kind of directly kill the PFAS, for lack of a better word. And so yeah, it's interesting. It's different, right?
Mm-hmm. Thanks, and I appreciate that additional explanation.
Sure.
Yeah, Max or Paul, anything else kind of from your perspective that hasn't gotten a lot of attention during the session yet today that you wanted to highlight that seems promising from your perspective?
I would say that it remains to be seen. There are a lot of technologies that can be aided with different types of catalysts potentially. And so there's, again, very academic research on understanding how different types of materials kind of interact with a lot of these different processes to help optimize or make them more effective. And those things are interesting. It'll be, we'll have to wait and see kind of how they play out, and the types of materials, if they become kind of more strange and esoteric, then it's kind of like, well, I don't know if we'll have enough. Can we scale that up? And so again, it's a question of, we see some promising results with catalytic or catalyst assisted reactions, but it's a question of, can this scale, or can this effectively treat multiple compounds simultaneously?
Yeah, and that's actually a nice segue into the question we had for you, Max, around that scalability. It came up in each of the presentations, and heard about a number of different challenges, but wondering if you can just kind of reflect again on the challenges around scalability and cost for some of the different technologies discussed, or opportunities. So are there kind of key things as you are thinking about scalability across the different technologies that really stand out to you as challenges or opportunities?
I mean, generally, so for the same thing would go for whether it's electrochemical oxidation or for supercritical water oxidation, where you're using we're not using, so I'll take SQO first. You're not using stainless steel. You're using a kind of a higher temperature resistant alloy. It's specified and kind of chosen and engineered, designed for a specific purpose and application. And so the question about scalability, that affects cost, because it's not a typical alloy that you would use, and kind of, you don't just go down to the hardware store and get it. It's processed from a manufacturer. And so so there are certainly considerations for cost in any type of facility, but you also have to weigh the cost of dealing with this problem, and kind of we look, without destruction technologies, we kind of envision that we would deal with PFAS in perpetuity. And so the idea here is that we have to put a cost on not doing anything versus a cost of doing something and destroying these compounds. And so I think any one of these technologies, building it up, deploying it, will take millions of dollars to see through. But the idea here is that you're creating a solution that would ultimately yield an end material that is in either relatively, or I would say, very low concentrations of PFAS, or kind of undetectable concentrations of PFAS.
Yeah, I would add to what Max said. I think that's one of the things we really hope that our numerical model will help us do is it currently has our 2 pilot scale combustors, full 3D reacting flow, but it also has a commercial rotary kiln based on one that actually is operating in Ohio. We have another one for a med path incinerator and one for a waste energy facility. And so I think an important part of the scale up is to try to figure out how could they try different operational tactics without having to test it on the real thing. And if we can show that our model is good at predicting our results from our pilot scale, and we had a field test at a similar facility that one of the other model is in, it will really help us answer the questions without having to actually perform the experiments with possibly expensive or difficult to acquire material. Like it used to be, everybody was asking us to take their AFFF off their hands. Now we can't get the stuff. And so we probably should have asked for more when we first got the chance to get it. But the scale up is crucial, and you may need to have tactics that don't involve testing it at full scale in order to do some of these scale up activities.
Thanks. Michelle, anything else from you to add to this, the response to this question?
No, I don't think so. I'm starting to look forward to, we've been responding to some of the questions in the chat, and I think looking forward to some of the other audience questions as well.
Yeah, well, that's maybe moving towards some of those questions. I just maybe start with thanking all of our participants for putting questions into the Q&A. It's, I know a lot of, yeah, it's just been great to see the exchange there. One of the questions that came in earlier in the webinar was around, we've kind of through the presentations and discussions so far have really focused on kind of the technical considerations like cost as folks are thinking about these different types of technologies. But how are some of the unintended consequences, such as impacts on the environment or public health, kind of from the use of these different destruction technologies, considered in the evaluation? So just wondering about the potential unintended consequences to the environment or public health.
I'm not sure I can adequately answer that. I would say that, in a lot of the evaluations, we do take into consideration the idea that we don't want to create something that is worse than the thing that we are treating. And so we try to examine a range of different, I'd say, compounds or parameters that are not just PFAS. And so while the PFAS concentrations inlet and outlet are kind of the interest, of most interest, we're also looking, as Paul said, something like hydrofluoric acid, where if you're putting in a lot of fluorinated compounds, the likelihood is that you're going to generate a lot of hydrofluoric gas. And so the idea is that you would want a gas capture system that was capable of handling that type of, that amount of material. And so there is consideration when we look at these different technologies, or even at the lab scale for our own health and safety, making sure that when we turn this thing on, that we're not somehow creating something that's worse. And so it's not all of those things are kind of published or detailed within the documents that we create, but they are considered. And so we do look, for things, again, like total organofluorine or fluoride, that would indicate when we cannot, so we kind of can synthetically envision that there are 9,000 different compounds, but we really can only quantify 50 or so of those compounds. And not all of those compounds are toxic. not all of those compounds have the same types of behavior or fate in the environment. And so the idea is prioritizing the ones within the agency that we do understand to have some toxic effects. And then, as things go on, we will get to those. But in the meantime, we use these non-targeted technologies like total organofluorine or fluoride to measure a defluorination effect, where you do see breakages of the carbon fluorine backbone, and that give us a sense that, okay, the products here are not PFAS. The products or byproducts are these other fluorinated compounds, and we can handle those kind of in our typical conventional filtration systems.
Yeah, I would add to what Max said, that one of the things that we're very interested in from a thermal incineration standpoint is the potential for mixed fluorochloral compounds, because many of for example, the waste energy facilities that are already probably processing PFAS containing consumer products, they're also processing chlorine containing consumer products. So we don't know how important they are from a toxicological standpoint, but they may be important from monitoring the incinerator operation standpoint. So that's one of the things we'd like to look at, is the potential for mixed fluorochlorocarbons to be formed, because that's a potential thing there that could make life interesting.
Thanks. Helpful to hear how you're thinking about some of the byproducts of the processes and how you kind of account for those in your work. And Max, I appreciate your point of, in the lab, also wanting to make sure that that's a safe environment, and that's part of what you're paying attention to as well. Thank you. Okay. So I'm not, there's one question that I wanted to ask here that I'm not fully sure I understand the question, so hopefully one of you will. But there's a question around what polishing remedial options should we be looking for in consideration of unintended HFA creation? Is that
not an area of expertise of mine, but I will jump in to say that there are HF scrubbers, out there. And so there's the equipment is designed to do this in other contexts. There's certainly other industrial operations where HF is generated as a byproduct and is managed. And so again, although it's not my area, that's what I would imagine, is that those approaches are carried over into these sets and settings as well.
Yeah, we use a wet scrubber on our research combustors. I'm not sure that a dry system might not be better, but I haven't seen any data on using those. But that the controlling of the emissions before it goes out to stack finally is a crucial piece of the whole puzzle.
Thanks. So, I think maybe building on some of these conversations around kind of the effects of the technologies and what the outputs might be, just wanted to maybe focus in a little bit more on the kind of byproducts of the different technologies and energy demands. I think I heard each of you talking a little bit about the energy as a factor. And so what will be left after the treatments, and are there other contaminants of concern, emissions, energy needs, outcomes, or outputs to be aware of?
I guess I'll jump in with the maybe the answer is a little bit of a cop-out, but I think a lot of that information is exactly what is emerging out of the research world right now. And I think that that one thing that's a little bit tricky is to try to, I think everyone wants to make comparisons of the different technologies, so we can say this one's better than that one. But it kind of depends on your set and setting and what your treatment objective is and what exactly you're treating as to what your goals may be. It may be worth it to use a very high energy system if it means you're going to end up doing it for a shorter duration, or you may choose to treat a high volume of water in a very passive approach, to concentrate that over a long period of time to make later approaches of destructive treatment more efficient. And so while we look for these answers, at the same time, I caution to anyone to overly generalize those answers as well, and to make sure that if you're trying to compare them, that you are doing so in an apples to apples situation. That being said, most of these approaches, because of the properties of PFAS, are energy intensive. And if they're not energy intensive, then they're going to be chemically intensive. There's, not yet biological methods or more passive approaches, I think, that we're seeing. It doesn't mean great people aren't working on it, because they are. But I think as of now, we can generally say that they are going to be energy intensive and or chemical intensive. They're going to be expensive. But when we start looking at some of the costs of health effects and what some of the trade-offs of not treating are, the cost side becomes more appealing on the treatment side of the table. So I know that wasn't the exact question, but
Yeah, I would just add to Michelle's point that there's a lot of focus at the moment where these destructive technologies are going to be probably energy intensive, just like incineration is. The hydrothermal technologies will still be energy intensive, but the goal is destruction. And so where we can either concentrate or reduce the volumes, that will be crucial to kind of how these technologies are used and deployed. And so, or material is removed from the system. So a lot of the idea here about using carbon as a filtration and capture system to treat a lot of the water and get a lot of the material, or using reverse osmosis membranes to treat a lot of material and reduce the actual amount of material that will end up going to one of these treatment systems, is kind of crucial to minimizing those costs and keeping these things in the territory of feasibility. If the idea is that we're going to kind of treat all of our it's not the idea here that we want to treat every drop of pumped groundwater with a SQO system or a plasma system. It's the idea is we want to have a treatment train in place that helps us kind of each step of the way, so that where we do use these energy intensive processes, we use them minimally and effectively.
Thanks. I think that really helps both think about, the reason for using these treatment technologies is because there is a kind of a PFAS in the environment posing a health risk that needs to be addressed, and thinking about how to sequence and combine the different technology approaches to reduce the overall kind of cost and impact of the different technologies as well. Michelle, it makes me think of one of the things I heard you say in your presentation around, there is no silver bullet. There's no kind of one, at this point, no one technology that will address all of the problems we're seeing, but rather, different technologies and options for different situations. There was a question, maybe a specific question about one type of contaminated media, but I would imagine that it's something that many of our participants have in mind when they're thinking about the PFAS contaminated issue around kind of the challenge of sludge and whether there's any technologies that have been demonstrated, tested on sludge and Paul. I don't know if that's something that you could speak to, or Michelle or Max, if you have any thoughts on that question.
We did do a field test at a multiple hearth incinerator, I don't know, 6 months ago. It's probably longer than that because the whole time frame over the last couple of years is kind of a blur. But we did do a field test of them processing sewage sludge in a multiple hearth incinerator, but I haven't seen the data. I think there's a report out, or at least it's under construction anyway.
Yeah, I think it's at the last stages, but it should be close. We have we kind of mentioned this before, but EPA has a lot of eyes on this, and so there's a delay in the work that we're doing right now. Kind of won't see the light of day for another year or so, and so we're trying, as we're doing research simultaneously to publishing research, and the research that's coming out now and that we're presenting to you now is from 2020 and 2021. So we're working quickly and actively, but it's also there are many steps in the process just to get the information out there.
Right, so something for folks who are wrestling with the sludge issue to keep an eye out for is that report. And maybe a follow-up question is, when these reports are released, where is it? The website that Paul shared earlier where folks should go for kind of finding them, or is there a central location on EPA's website where you're publishing the results of these studies?
It'll be on several places because these are high visibility activities, and so they'll have it on. They'll obviously put it on our PFAS treatment page that I showed. It would be in our EPA science inventory. That's the main clearinghouse for various technical publications. I don't know if there's a mailing list or to send people information when these things do come out. I think keep an eye on the social media pages maybe, but we try to advertise them when some of these come out. It's just it's not always the easiest. You can lead a horse to water, but you can't make them drink. Stuff is on the internet, but knowing where to look is hard. But that one page that was shown in the presentation, that would certainly be a location where, if any of these reports are released, or we'd put them up there.
And then I would say, you can reach out. We gave contact information. We can always kind of pressing a lot of the contact us buttons on EPA does actually put you in touch with people, and they will get you to the right people. And so I think people are constantly surprised that we do respond to those things. And also I would, if there are, if links take you to a journal article or something like that, where you can't kind of easily access it, you can always reach out to us directly and we can get you those things too. Don't tell the journals I told you that.
Thanks, appreciate that. So one other question that came in is around just building on some of the things that we talked about so far. The question is that current pyrolysis infrastructure seems to have contributed to PFAS contamination. For example, PFAS contaminated biochar being spread on agricultural fields. And just the question is whether pyrolysis of PFAS for destruction will require new pyrolysis technology or additional capital expenditure, or can current systems be kind of tuned for PFAS destruction?
Yeah, I can kind of answer that. I wouldn't say I'm the best, and we don't have a lot of pyrolysis systems within the United States, so it's in any case, I think in most cases there might have to be some adjustments if the goal, because the goal generally with pyrolysis systems is not to treat PFAS, it is to generate either a syngas or a biochar. And so if the purpose is something different where it's treating a contaminant, then I think there will need to either be some tuning or some other capital outlay that kind of refines or optimizes the approach, but I wouldn't think that you would need to kind of buy a whole new system. I say that on a gut level, but I can't say that for any of the folks that are actually operating pyrolysis units out there.
Yeah, I would add that I think for any commercial facility, their first choice would be to not have to radically change their operating procedures. So we've been in our research focusing around the standard operating environments that commercial incinerators have, and we're trying to mimic that the best we can in our experimental facilities, because most facilities are not only going to be processing the PFAS waste, they're going to have 100 other things that come in through their routine operation that they have to properly operate as well. So, the idea is hopefully we can get it to work using as much of the standard operating procedures that they already operate under.
Great. Thanks. I want to circle back to, maybe something you mentioned, Paul, earlier in your presentation about your interest in getting AFFF. Could you say a little bit more about why that's something that you're interested in and what you're looking for?
Well, we're trying to do the experiments with actual AFFF now, and we need on the order of, I don't know, milliliters per minute to do the experiments, but we usually need to run it for 2 or 3 hours if we're doing some of the, like OTM 45 is one of the new test methods they're coming up with for measuring incinerators, and you have to essentially suck a meter cubed of stat gas into the sampling train in order to satisfy the method. And so we thought that, getting a 5-gallon bucket was enough last year, and we've gone through that. And now everybody who had many 5-gallon buckets before, now they don't have any. So it's we're trying to find the legacy AFFF that hasn't had the formulation change. So we're looking for stuff with the C8 and C6 PFAS in it, and it's just not as easy to come by as it was a year ago.
Interesting, and thank you for sharing a little bit more about that detail. It kind of stood out to me in your presentation. So there was one question that I believe was answered in the Q&A, but also might be something that I imagine many folks who are participating in the webinar might be curious about, and that's maybe something, Paul and Max, you can speak about, is just as there are new PFAS destruction technologies coming on board, and locations are looking to utilize some of them. Do you know if there's any EPA approval required, or before a state or local community might adopt and use that technology?
I don't think there is at this point. My guess is, and this is purely a guess because we're researchers, we're not the policy people. I know that the policy people are spending a lot of time thinking about how they would deal with regulating the PFAS, but my understanding is that the Clean Air Act and RCRA have largely been delegated to the states. So I think what probably might happen, and it's kind of weasel words, but that's probably all we got right now, is I think the primary decision makers are still probably going to be at the state level for giving people permits to burn the materials if they're regulated under these laws. But I'm sure the EPA will be working to come up with guidance to support the regulated community on how to do this properly based on what we know from the science. But my guess is primarily the regulatory emphasis will come out of the States, but I could be totally wrong.
Thanks, Michelle. I think I saw you kind of moving your head and in agreement. Just want to check to see if there's anything else you would add.
There, I had to find the unmute button. My scroller ended up over. No, I guess I'm just, nodding in agreement.
Okay, great. Well, thank you. And thank you. That kind of brings us to the end of our the time we have for Q&A. So I just really want to thank our presenters for your presentations, and then for your thoughtful consideration and responses to a lot of the questions that have come up, both verbally and in the Q&A part. I know there's been a lot of activity, kind of typing responses there. Just in the closing few minutes here, just wanted to see if Michelle, Max, Paul, if you have any kind of closing thoughts for our participants as we're winding up here.
I appreciate everyone listening. I know it feels like, we continue to listen to things that are coming down the pipeline, right? And everybody's waiting for that thing, right? That's actually going to come out and be the fix. And I guess I would just say, look for the thing in many different directions, and look for different solutions for, for sediments and for sludge and for water and for air. Keep asking the good questions about byproducts and energy demand and environmental justice. I think we're all trying to get there. We might be the technical audience today, but I think we're in it for the reason to protect public health.
I would add that keep an eye on the EPA website, where they talk about the PFAS and their development of any sort of rulemaking procedures that they're going through, because there's always a commenting period where they want technical and policy comments from the stakeholders. So I think keep an eye out for that, because there will be an opportunity to comment on any proposed rulemaking that they do. And it looked from looking at who's in the chat that a lot of the attendees of this webinar would probably have some good comments to pass on.
Thanks. Okay. Well, as we're wrapping up here, just a few notes from me, and then I'll turn to Rebecca for any kind of final thoughts. But first, we're going to put up a brief post-meeting survey poll. So just a quick poll with a few quick follow-up questions. There will be a kind of a longer survey that we send by email, but we really value, for everyone who's on today, value your input into and feedback on the event. We're always trying to look for ways to grow. So your input on the survey would be really helpful. As I mentioned earlier, we will be sharing both either by email and posted to the Epicenter website. The recording, attendees will receive the answered questions and the chat. So that's, you don't have to kind of capture all that now. That will be shared by email. And then we are also going to host, there's such a robust question and discussion, and we know that there are limitations to the webinar format. So we are going to host a follow-up meeting on Thursday, October 20th. And there'll be a link to register for that in the follow-up email. And that will be an opportunity, a more informal session for questions and technical discussion with our panelists. So keep an eye out for that. And if you're available and want to continue the discussion, invite you to join. So thank you again to our panelists for your really in-depth and wonderful presentations, and to our participants for joining. Rebecca, any final closing thoughts from you.
Thank you. It was wonderful to hear from all of our panelists and the questions and chat. And I encourage anybody who would like to join us on the 20th of October to have the chance to really get into the details and answer any questions that you still have. So thank you all. And we encourage you to fill out the survey and help us do better with all of these events.
Thank
Take
you.
care.
Bye.
Thank you.